Hey everybody, I'm Oben. This is Patrick and Ashley. We'll be talking about finding patterns in the clouds today, specifically cirrus clouds and specifically a spiral pattern that I'll explain. I'll get into. I don't think I need to sell anybody on the idea that clouds are important and part of climate, but like Marcus said in his talk last week, there's a lot of uncertainty in clouds, both introduced by the scale, but also in the processes. There's a lot we don't know about processes, and specifically cirrus clouds. Here are cirrus clouds over a New York skyline, are made out of ice crystals. And these ice crystals have a ton of diverse shapes, behaviors, and lifetimes. Here's some imaging of ice crystals, very teeny ice crystals stolen from cirrus clouds. And they're, so a recent kind of state of the science approach for simulating clouds is Lagrangian cloud models or particle-based models where they track cloud droplets or cloud particles as they travel through the atmosphere. And a paper that just came out last month finds that a lot of the variability in these ice crystals actually comes from where they've been in terms of how much relative humidity they pass through on their wildly diverse and heterogeneous trajectories. This is the first Lagrangian cloud model, which is paired with a large eddy simulation for driving the dynamics forward for cirrus. And this is a really rich data set of a ton of particle trajectories for us to study ice crystal evolution. Problem is, that's a lot of trajectories. So we're interested in seeing if there's some sort of smaller amount of representative trajectories. And so what we just started with was doing k-means clustering on these trajectories, these thermodynamic histories that the paper says contribute most to the variability in these ice crystals. And the fun thing about applying k-means clustering on a time series where we treat every 35 time step 35 time steps, treating every time step as a dimension, is that the centroids of these clusters are also interpretable as time series themselves. So we get representative thermodynamic histories from these centroids. And we see one characteristic trajectory that starts very saturated, but then ends in very subsaturated conditions below 100% humidity. And we find these clusters just on thermodynamic histories alone, but we can look at the averages of those clusters with other environmental variables. So we clustered on relative humidity or supersaturation, finding that these clusters are actually in different places in the cloud. They have very different radius trajectories and also their density changes. And in fact, one of these clusters just turned into pure little ice balls at the end of our simulation. And here's some evolving size distributions of our 4 clusters. We tried doing more clusters and after 4, they all just started becoming different combinations of these. But what we see is that this cluster 2, this blue line, starts actually in pretty highly saturated conditions and is large, but towards the end falls out of the cloud. What's even more interesting is when we applied PCA to these trajectories. So going from 35 dimensions that correspond to relative humidity at 35 different time steps to just 2 principal components, we saw that the clusters that we got from the k-means are all different coherent parts along some sort of curve, right? This 1D manifold. And it's like a Rorschach test for scientists, right? What shape do you see here? And I already had it in the title, so I gave it away. But Kara proposed that we fit a spiral curve to this. So then we could just have one parameter that we crank around the spiral to explain the different trajectories. And it's really interesting that the parameters in this equation, one of them converge to essentially be phi, the golden ratio. And so the black one is our, letting our parameters run freely. And this gold one is letting one parameter, just a scaling parameter, run freely, and snapping the other one to our golden ratio, our like Fibonacci sequence, our shells. Pretty cool. I'm not sure if this might be just a neat coinky dink, not like a fundamental explanation for it or anything. And that's all right. That might be still a useful qualitative descriptor of whether or not, so this theta parameter that controls the spiral, whether or not the cloud particles will drop out of the cloud. There's some text on this. Let's see if I go forward. There we go. And so the climate relevance is that, these clouds, which are made out of a ton of ice crystals, the cloud interaction, it's radiative forcing, and its lifetime is influenced by these crystals' paths and lifetimes. And maybe we can use theta as a single parameter that explains the diversity of the lifetimes of these crystals in these cirrus clouds. And that's pretty much all I have. If you're thinking, Oben, this is Leap Dude, and where's the deep learning? We got you. Patrick and Ashley are gonna have both used neural networks for two different parts of this project. Patrick's gonna talk about a survey of clustering algorithms and unsupervised algorithms, analyzing these trajectories. And Ashley's gonna talk about using a neural network, a supervised neural network, to predict the evolution of crystal growth given these trajectories. So that's all I got. I'm actually going to stop here for one question before we move on to Patrick and Ashley. Yeah, all you, Anthony. Nope. Okay. Click on the draw.
Just really quickly, for the sake of my clarity, when you say you apply k-means clustering to a time series, when do you do it? Do you do it to like the initial distribution, and then you just assume that those points will remain in that same cluster? Do you apply it at each time step in the evolution? And if so, you're not guaranteed to get the same points in the same cluster if you apply it at each time step, right? Did that make sense?
It totally makes sense. This is kind of a non-standard use of clustering in that every time step we're treating as a feature. So it's a dimension. And the different observations, the different data points are these particles themselves. Great question. It's a confusing use of k-means, but I think it's kind of neat. Anyway, over to you, Patrick.
Thank you, Oben. Yeah, so I chose to go like with my research on trying to answer questions about which clustering methods are most effective on this kind of data set, on these trajectories. And so I started by taking like the massive data frame of all the variables, all the time steps, all the super droplets, and just looking at one variable, which was relative humidity. Across all the time steps for all the super droplets, and then running a survey of clustering methods on that variable. And so like initial results of just running all these different clustering methods were that k-means and spectral clustering were particularly effective. I have a table here with silhouette score and CH score, which I'll talk about briefly. Silhouette score ranges from -1 to 1. Higher the value, the better. If it's above 0.5, it's considered pretty good clustering. CH score is a little more complicated. There's no kind of like threshold that CH score could reach, which denotes like a good clustering. But generally higher is better, and it's useful to compare across like similar clustering methods to see how they compare against each other. Yeah, so that was the initial results. I then decided to use an autoencoder, which compressed the data down into a lower number of dimensions. We had a 35-dimensional array to represent the trajectories before. But by using this deep learning method, which could find nonlinear relationships, we can get it down into a 2-dimensional latent space, which I have plotted here on the left. And then what I did is found k-means clusters within that latent space, which you can see denoted by the different colors there. And then after going back to the actual 35-dimensional space and applied those centroids and labels to the droplets within that 35-dimensional space, I was able to plot the trajectories of those centroids on the right. And I got much, much better results on these metrics. You can see the silhouette score is around 0.8. It was like 0.4, 0.5 before. And the CH score is orders of magnitude higher at 100,000. Yeah. Another interesting result of using this autoencoder is present when we look at the representative deciles of the latent space. So these are like reconstructions of all the deciles of the latent space and what kind of trajectories would look like in those areas of the latent space. And what was interesting is that all of the variance we have is basically contained within Z1, and there's very little variance in Z2. Which is a similar result to what Oben got using his spiral, in that we can find like a one-dimensional kind of space to represent all the variance on these within these histories or trajectories. And yeah, my final kind of interesting conclusion was found when I was trying to set up my latent space. I was trying to determine how many latent dimensions I should use to represent and scale the data down into. And Joe recommended that I use a library called UMAP to kind of project the data when it is in these like 16-dimensional spaces to try and visualize it. And when I was projecting it and comparing it with a much lower dimensional latent space, we learned that there wasn't a lot of like disparate clusters that were generated when we projected it, and we weren't gaining a lot of detail. But that in both cases, we have these kind of continuous shapes that are formed when we project this data through UMAP, which is again kind of another reason or another piece of evidence toward the fact that we can find some way to one-dimensionally represent these trajectories. If we can map along these shapes, like there obviously are complex shapes, they're not incredibly simple, but if we can map along these, we can represent all the variance in these histories by just one dimension of just how far we travel along these shapes. But yeah, that's the findings I had. I'll give it off to Ashley to talk about making predictions on the data.
Hi everyone, I'm Ashley, and so this summer I researched on emulating the Lagrangian ice crystal evolution in cirrus clouds using supervised machine learning models. So what Oben mentioned a bit earlier was about the Lagrangian LES large eddy simulation. And so this is the current model used to represent the cloud evolution and formation. However, this type of model is very timely and computationally expensive. So approximately like 300,000 core hours are used to run a single simulation, which makes this not a very viable option to sustain researching in ice crystal evolution. And so what I'm trying to look into is whether or not supervised machine learning model can serve as a substitute emulator and representing the ice crystal evolution. And so I guess like the biggest chunk of this project that my project and I work with is just like exploring the data, since we are kind of the first ones to work with this data set. We did a lot of exploratory data analysis. And so like on the right of or actually on the left, You can see like the distribution of the radius sizes in over the 36 time steps. And then part of the exploratory data analysis was also cleaning the data. So we combined the trajectory environment to data files. And then for my specific project, I looked into predicting ice crystal evolution with supervised learning. And so I used 10,000 superparticle samples. But before I even delve right into supervised learning, I wanted to check and identify like the specific features and targets to use. And so I created a correlation heat map to kind of see which coefficients were the highest. And so I ended up using the 6 features being temperature, relative humidity, pressure, mass, radius size, and deposition density. And the targets being change of mass and change in radius. And so the first model that I work with was multilinear regression with a single time step prediction. So with the 6 features and the 2 targets, I evaluate the performances being very poor with 0.56 and 0.62 respectively in R-square for change of mass and change of radius. And so this kind of makes sense because multilinear regression, they're not really great at, or they can capture, but it looks like it's not good at capturing complex relationships of the particle's microphysical properties. And so this kind of helped solidify to not go with regression and understand like the ice crystal evolution. And so I guess the next thing, oh yeah, and then I also did single time step prediction. So I'm predicting the next time step of like the initial time step. And so with the next model that I work with, which is the fully connected feed-forward neural network, the performance with this is a lot higher, with the R-square being 0.95 and 0.89 respectively for change in mass and change in radius, which is great. And it also makes sense because it can capture complex nonlinear interactions a lot better between the features and targets. And after doing like the single time step neural network, I wanted to kind of solidify the features and targets before moving forward with the more complex modeling. So then I also looked into like SHAP, which provided importance of like the features of like after the prediction. So it looks like relative humidity with respect to ice and the mass being like a really good indicator for these features to be used in making decisions about the relationships of the ice crystal evolution. And then the last model that I worked with was the multi-time step prediction. So basically I took the single time step model from like the initial neural network and kind of roll it out for like the multiple time steps. So it's like you're taking the output of the single time step or like the initial time step and you're using that as the input. And so then it'll be like a cascading kind of effect. And in this part, my mentor Joe really helped a lot in this part because I had some debugging issues that I couldn't quite figure out. But what we figured out was the R square of all the time steps declined a bit over time for both change in mass and change in radius. Um, it looks like it's like even though the accuracy is declining over time, it's not too significantly declining, which still makes this type of model still promising to work with. And then onto your left, there the model, I plotted the 4 random superparticles. So you can also see like the accuracy and the predictions, the true versus the prediction of the mass and the radius over time. So it's kind of like you're getting to see like the specifics of the particles over time. And that concludes my presentation. Thank you.
Oh, really cool. And I'm not just biased because I like clouds and microphysics. I was wondering, or did you guys try the k-means clustering with variables other than supersaturation? It looked like you were mostly tracking altitude in some of those plots.
Yeah, we only did supersaturation, mostly informed by the kind of conclusion of Kamal's paper that came out, which is that it's the main driver of the variability. We did like concatenate other variables. What did we concatenate, Patrick?
Supersaturation and droplet radius.
Yeah. And so and like particle radius, right? And it did it? I think it didn't change the actual shapes of the clusters in either dimension much, from what I remember. So then we stopped looking at it.
I echo that. I think the fact that the trajectories can like lie on the 1D manifold is like really, really cool. I was curious what this like unsupervised thing is like descriptive or like predictive in the sense of when you were saying with like the things falling out of the droplets. Is it like the first 35 time steps are sufficient to then kind of track the rest of the lifetime history of the droplet, or it's like whether it falls out or not is like within those 35? So are you using the representation of 35 time steps to try to make other statements, or is the main insight just that like the trajectory itself is just really well described by one number, which is in itself really cool?
Yeah, the short answer is descriptive, not predictive.
Great. Thank you so much.